All right, guys, so everybody has a note sheet, yes? You'll need one of each calculator.
I have one calculator.
It'll be good to have both calculators. Now, before we start the note sheet, we're going to look at one of the homework problems, problem number 16. I want to look over problem number 16 from the homework. Now, problem number 16 looks like this here. So we have p minus 4 squared equals 49. Now, we can solve this problem by the square root method. And the first thing we'd have to do is get the set of parentheses, our term being squared by itself. Now, if we had anything added or subtracted from the parentheses, so if we had plus 7, we would minus 7 from both sides. If we had minus 6, we would add 6 to both sides. We got to get the parentheses by themselves first. Since there is no number being added or subtracted, we won't have to do that there. If there was a number, say, multiplied in front of the parentheses, we would have to divide both sides by that number to get the parentheses by itself. Now, luckily for us here, the parentheses are already by themselves. So that means we can go on and take the square root of both sides. And on the left-hand side, our square root and square would cancel, leaving us with p minus 4 is equal to plus or minus, because we took the square root of both sides. Now, the square root of 49 is going to be 7. Because 7 times 7 would give us 49. At this point here, we need to finish getting p by itself, solving for the value of p. So we would add 4 to both sides, and our negative 4 plus 4 would cancel, giving us p by itself. Now, when we add the 4 to the right-hand side with the fact that we have the plus or minus, we're going to put the positive 4, the plus 4 in front of the plus or minus, and the 7 stays behind it, telling us that p is equal to 4 plus or minus 7. Now, are we able to add and subtract 4 and 7? Are they like terms? Here's 4 and 7. Are they like terms? Well, they are, because we can say 4 plus 7. Well, 4 plus 7 is 11. Go in the other direction. 4 plus 7 is 11. So we can say p is indeed equal to 11. We can also do 4 minus 7. And 4 minus 7 is negative 3. So if we are able to add and subtract, we're going to have to add and subtract. We're going to have to combine those like terms to simplify now. So I wanted to show us this here, show you all this here, work through this here. So we do see an example of this, the fact that we can add and subtract these like terms. Now, picking up where we left off yesterday, the fact that we can't find the square root of negative 5/2, we came up with this error, this doesn't work. So, what we're going to do, all right guys, is we need to find a number when multiplied by itself gives us a negative number. Because no matter what we do, when we multiply a number by itself, say even 2, because 2 times 2, 2 squared is going to give us positive 4. Negative 2 times negative 2 is still 4. When we multiply a number by itself, we still get a positive number. There's no way to multiply a number by itself and have it be negative. So we're going to have to imagine this number, this I squared, this number being multiplied by itself, giving us negative 1, giving us a negative number. We have to imagine, we have to come up with this, because otherwise there's no way for us to take or find the square root of negative 1. But by this here, how we have this set up, the fact that I squared equals negative 1 means that I is indeed equal to the square root of negative 1. This imaginary number, I, will be equal to the square root of negative 1, and that is what I is, our imaginary number I. To be able to solve these and simplify these radicals, to find this number when multiplied by itself gives us a negative number, we have to have the imaginary number I. And I is equal to the square root of negative 1. And now that having this and knowing this, we can actually start simplifying these radicals, these square roots, with negative numbers. So if we take the square root of negative 25, for instance, we can actually break this apart because the square root of negative 25 is the same as saying the square root of negative 1 times 25. Negative 1 times 25 is negative 25. Now, according to our properties of radicals, if we have two things multiplied together inside a radical, we can actually break it up into two separate radicals. So really, the square root of negative 1 times 25 is the same as the square root of negative 1 times the square root of 25. And we can simplify from this here. Now, the square root of 25, we can simplify that quite nicely because we're trying to see what times itself is 25, and that's just 5. Now, the square root of negative 1 is I. I, this imaginary number I, is by definition the square root of negative 1. So this square root of negative 1 here is just I. So we're able to find out what the square root of negative 25 is. It is 5i. 5i is this imaginary number because there is no real number that multiplied by itself gives us negative 25. But by using these imaginary numbers, these I terms, we can find what the square root of negative 25 is, and it is 5i. Questions on this so far? Question on anything we've done so far? Now we look at the next one, the square root of negative 72. We can do the exact same thing we just did. We can consider the two main parts. We have the negative 1, our negative part of the square root of 72, and our 72. Again, we can break it up into negative 1 times, square root of negative 1 times the square root of 72. Now we can simplify the square root of 72. We've got to find the perfect squares that make up 72 and simplify those out. Or we can use the 30xs and say square root of, not 76, 72. And it'll tell us that it's 6 square root of 2. And the reason that this works is because 72 is 36 times 2. Square root of 36 is 6. And we can't take the square root of 2, so it's just the square root of 2. Now, by definition, square root of negative 1 is I. So our square root of negative 1 is just going to simplify to I, telling us that the square root of 72, square root of negative 72 is 6i square roots of 2. Questions on this here? Now the graphing calculator can do some of these here. So if we said second square root negative 25, it will tell us that it is indeed 5i. But the only way it does it is if it is in the mode a plus bi. It has to be in or set to a plus bi mode. If it's not, it will tell us that it's non-real zeros. Because if it's set on real, instead of a plus bi, when I take the square root of negative 25, it'll tell us non-real answers. And that's true because 5i is not a real number. It's not a real answer for this here. In real mode, all calculations must result in a real number. So we can just say quit. Now to change it, we have to go to mode and scroll down to where it says real and go over to A plus BI and hit enter. We have to switch A plus BI on. Because once we have A plus BI turned on, we can tell it the simplified negative square root of negative 25, and it'll tell us that it is indeed 5i. Well, that means probably we can do the next one. Second square root negative 72 is 8.48528137 I. Well, that's not exactly what we got. We got what? 6i square root of 2, yes? Well, those are the exact same numbers, but we want it in simplest radical form. We don't want it in a decimal approximation. So we're not able to get directly there. So we might be able to use the 30xs, second square root negative 72 is domain error. So the 30xs can't find the square root of negative 72, but it can find the square root of 72. So we might be able to use it to find and simplify these here. Now, if we look at the next one, negative 5 times the square root of negative 9. So we have the negative 5. So we'll need to multiply it by the square root of negative 9 once we simplify it here. Now, what have we noticed with this negative inside the radical? This negative 1, we're able to pull it out. We're able to change it into I. Because whenever we have that negative inside the radical, we could really say it's the square root of negative 1 times the square root of 9. Square root of negative 1 by definition is I. Now we just need to take the square root of 9. And what times itself is 9? Would be 3. Negative 5 times 3i, negative 5 times 3 is negative 15, and we have I. Questions on these first three here? Let's look at the next one. We have square root of negative 4. Well, as we just said, this negative 1 inside the radical is going to come out as what? All right. It's going to come out as I. Now, what that leaves us with is just the square root of 4. And our square root of 4 would reduce to 2, telling us that the square root of negative 4 is 2i. If it reduces nicely, the graphing calculator could have done this for us. Second square root of negative 4 is indeed 2i. Our next one's the square root of negative 12. So this gives us a decimal. We know it's going to have I, but that's telling us that this 12, the square root of 12, does not reduce nicely. It's still going to have numbers left over inside the radical. But what we can do is that we do know this negative is going to come out as I. That negative is going to come out as I. And what that leaves us with inside the radical, or what's left of the radical, is the square root of 12. At this point here, we can take the square root of 12. We can simplify it. Look for perfect squares. Perfect squares with 12 would be 4 times 3. Square root of 4 is 2. Square root of 3 does not simplify. Telling us that we have 2i square root of 3. The 30xs would do the square root of 12, telling us it is exactly 2 square roots of 3. We just have to put the I back in. Questions on how we simplify these radicals here? A lot of these are very simple cases, easy ones we can do on our own. There are others that we could do. We're not going to focus too much on those here. Now, the last two we have here is negative square root of negative 36. Well, the negative is still part of this. It's outside. So the first main part we're going to look at is the square root of negative 36. We know that the negative inside the radical, this negative 1, is going to become I. Now what that leaves us with is what? The square root of 36. So what is the square root of 36? It is 6. So we have negative times 6i, which would be negative 6i. Questions on this here? And our last one, 2 times the square root of negative 54. So we still have our 2, and it's going to end up being multiplied with whatever the square root of negative 54 simplifies to. Now the negative, again, we know that it's going to come out as I. Now we just have to see what the square root of 54 simplifies to, which would be 3 square root of 6, which means the square root of negative 54 would be 3i square root of 6. Last but not least, we'd have to multiply this together. 2 times 3i would be 6i. We still have the square root of 6. Questions on this here? Questions on simplifying i's, our powers of i's in these radicals? All right. Next thing we're going to look at is powers of I. Now, so far what we've said, by definition, I is equal to the square root of negative 1. And the way we got there is we really started off by saying that I squared is this negative 1 number. So we knew to get there, we're just saying I squared is negative 1, so we can actually simplify powers, or simplify radicals with negatives. From there, we're able to get that I is equal to the square root of negative 1. Now what we want to do is we want to look at higher powers and see if there's some pattern, something that works with these powers of I. Well, I cubed is the same as I squared times I. Now the reason I'm using this here is I don't want to have to multiply I by itself 3 times, especially if I know that I squared is negative 1. So if we take I squared times I, well, I squared is negative 1, giving us negative 1 times I, which is negative I. So I is negative 1. I squared is negative 1. I cubed is negative I. So far, not a whole lot that we've said or seen this here. It's not that bad. I to the 4th. So again, we're just multiplying by I again, which is telling us that we have I to the 3rd times I. Because again, we're taking what we know and multiplying it again. I to the 3rd. We've already shown that it is equal to negative I. So we replace I to the 3rd with negative I, telling us that we have negative I times I, which is going to be negative I squared. And I squared we've already found. I squared is just negative 1, telling us that we have negative 1, which is just 1. Which means I to the 4th is positive 1. We're going to keep going. We're going to go to I to the 5th power. Well, as the pattern we've been using, we can say that we have I to the 4th times I. Again, I to the 4th, we've already said what it is. I to the 4th is 1. One times I is I. Okay. Then we're going to keep this pattern going on. We're going to do I to the 6th. Well, I to the 6th, we can say is I to the 5th times I. And as we just found, I to the 5th would reduce, I to the 5th power would reduce to I, giving us I times I, which is I squared. And we know that I squared is negative 1. Now we're going to move to I to the 7th. I to the 7th is going to be I to the 6th times I. Well, I to the 6th we already found. I to the 6th was negative 1. And negative 1 times I is negative I. I to the 8th. Does anybody have a guess at what I to the 8th is? You all know? Because I to the 8th, we can write as I to the 7th times I. Well, what is I to the 7th? Negative I. Negative I times I would be negative I.
If you use negative I from minus 7 times I.
Because I to the 7th, we figured out, because anytime we multiply powers together, I to the 6 times I, multiply like bases, we have the exponents. That is I to the 7th, yes? Well, let's go back up. Because we started off with I squared, which is negative 1. We're good there, yes? I cubed. Well, we're multiplying I by itself 3 times. Trying to say I squared times I. Well, we know what I squared it is. So I'm going to replace I squared with negative 1. Negative 1 times I is. Okay, we're going to look at power 4, I to the 4th. Well, I to the 4th, we can say is I cubed times I, yes? Now we use I cubed because we figured out what it is just a second ago, yes? I cubed is what? Negative I. So I'm going to replace I to the 3rd with negative I, which gives us negative I times our other I. I times I is negative I squared. We get the negative from there already. I times I gives us I squared, yes? Well, we already said what I squared is. I squared is negative 1. So what I really have is negative 1, which is just 1. We get up to 4. So the 5th power, we're just multiplying it again, and we get this here, which ends up getting us to I. I to the 6, we do a similar method, get to negative 1. I to the 7 ends up getting us negative I. I to the 8th ends up getting us to 1. Now the question is, can you tell me, or take a guess at what I to the 9th is? Right? Well, I to the 8th is, so 1 times I is, Anybody have a guess what I to the 10th is? Negative 1. Because where did we start out with? We started out with I, yes? And when we squared it, what did it simplify to? Then we did I to the 3rd, it simplified to and then 1. Then our next one was what? Then and then this simplified to I. This would be yes. And it repeats this way every single time. And that's actually kind of interesting. It's kind of interesting the fact that even though we keep multiplying by powers of I, no matter what it is only is going to become one of 4 things. It's either going to be I, -1, -I, or 1. Now, a way that we can find this with any power of I, doesn't matter what it is, I to the nth power, we take whatever that power of n and divide it by 4. And if we're focused on the decimal, if the decimal number is 0.25, that power of I is going to simplify to just I. If the decimal is 0.75, or 0.50, we skipped one, it would be -1. 0.75 would be negative I. And 0.00 is going to be 1. So with our powers of I, for any I to a given power, we're going to take that power and divide by 4. If the decimal is 0.25, it's going to reduce to I. If the decimal is 0.50, it's going to reduce to -1. If it's 0.75, it's going to reduce to -I. And if the decimal is 0.00, in most calculators, it's going to divide evenly. It won't give us a decimal number, or 0.00, just give us a whole number, an integer. It's going to reduce to 1. And this works with positive powers of I. So let's look at the first one here. I to the 27th is what we want to evaluate. We want to see what is this going to simplify to. So what we can do is we can take the power of 27 and divide it by 4. What do we get? 27 divided by 4. 6.75, 6 3/4. We don't really care about the 6. We want to look at the decimal, 0.75. And it's attached to what? -I. So it's telling us I to the 27th power reduces to -I. Now, the only thing the 6 tells us is this cycle of 4 terms, I, -1, or I, -1, -I1, we went through that cycle 6 times. We went through a full 6 rotations of it, and we went 3 more. So if we look at I to the 34th power, really what we can do is divide 34 by 4, yes? So that would be 8.5, which tells us that it is indeed -1. 47 divided by 4 is 11.75. So this would reduce to -I, yes? And we can keep doing this here. Academics, because these questions do show up in academics. Now, the nice thing with this here, if you're don't have a calculator, luckily for y'all, you will for in class, we can look at the last 2 digits. Because if the last 2 digits divide by 4, the number itself divides by 4. Now, if I look at 40 or 65, 40 would go into it nicely, giving me 25. 28 is one of the ones I know that's close to 65, or because it would be 68. It's 3 off, which means it's going to be I. Or we could say 64 would be another one that's divisible by 4. It's one below it, or one above it, so it's going to be I. So does that make sense? It's might be confusing for some, but You're trying to get how far am I away from the next divisibility of 4. Or if we have a calculator, because it'd be 13.75? 25. I had the wrong number. Or number here. Because 0.25 would indeed give us I, yes? Now the last one, I to the 1040. 1. Because even though we have a big number, is 4 divisible by 40? There's 40 divisible by 4. 10, yes? So it divides evenly, telling us it is 1. Grab the graphing calculator. Go second decimal. Second decimal. Second, and then our decimal point. It gives you an I. Now they do the little hook on it to signify that we're talking about the imaginary number I, not the variable I. Now, the one that we did before the last one was I to the 65th power, yes? What was it? It was I, yes? We also did I to the 27th, which was negative I, yes?
I got negative 1.5e minus 12i.
You did 12, or I to the 1040?
I did I to 6i.
So it gave you something like this here, yes? Like mine on the last one? Or
Give me that.
something similar to this here, yes? So it totaled 1 plus 4e negative 12i, or it probably gave you something like 4e to the negative 12 plus I, something like this here. Now, what that's telling us is they rewrote it in scientific notation. The e is really saying that we have 1 plus 4 times 10 to the negative 12th power times I. This number here, 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's really telling us that we have 1 plus this number here. Now, with higher powers of I, the graphing calculator actually graphs it using the graphing feature to find out what the power of I is. This number here is so infinitesimally small. For us here, this is just 0. Because again, it's graphing, so it's looking at the pixels on the graph and is having to approximate. And once we get to such a big power of I, we have a pixel error that starts coming into play. So for some powers of I, the graphing calculator can do it simplified just fine. But when we get to these bigger powers, 1040, it might be easier just to divide by 4, figure out the decimal, and go from there. So we're not having to figure out this funky e to the negative 12. Questions on this here? Sum and difference of complex numbers. To add or subtract two complex numbers, you add and subtract the corresponding parts. A complex number comes in the form of a plus bi, where a is the real part of it and bi is the imaginary part. So, when we look at the first one here, 8 minus I plus 5 plus 4i. Now the 8 minus I, there's nothing in front of the parentheses, so we can go on and drop it, and then we have 8 minus I still. Since we have a plus in front of our second set of parentheses, we can go on and drop it. We don't have to distribute a negative if we're subtracting. And we get this here. Now the real numbers are what? 8 and 5. There are numbers without I. So we can put them next to each other. We have 8 plus I, 5. And we'll put our negative I plus 4i next to each other. Focus up here. 8 plus 5 is 13. Now the question is, what's negative I plus 4I? Let me rewrite it. So if I asked you what negative x plus 4x is, what would it be? No. Negative x plus 4x? Negative 1 plus 4? B? 3x, yes? Because we're just subtracting those two. So what would negative I plus 4I be? Mm-hmm. Yeah, that's it. Because for the most part, we can treat I like we do most variables. The only thing that we can't do with variables is if I gets a power greater than 1, we have to simplify it. Variables, if it becomes x squared, x cubed, x fourth, we leave it, it's fine. So here we get 13 plus 3i. If we look at b, 7 minus 6i minus 3 minus 6i, we can drop the parentheses with the first. It's still going to be 7 minus 6i. Now with the second one, we've got to distribute this negative 3, which is going to turn our positive 3 into negative 3. It's going to turn our negative 6i into positive 6i. We can move it around and get our like terms next to each other. So our 7 and negative 3 are like terms, so they'll go together, and 7 minus 3 is 4. What is negative 6i plus 6i? 6i minus 6i is 0. 6 minus 6 is 0. So those are 6 minus 6 is 0. So it's just questions on this here. (13 minus quantity 2 plus 7i plus 5. What was it? Plus I? 7i. Thank you. I. And then it was plus 5i. 11 minus 2i, because if we work this out, 13 minus 2 is indeed 11. Negative 7 plus 5 would be negative 2. We still have our I. And that's it. I think we feel pretty comfortable with these here because really we're just dropping parentheses, distributing, and combining like terms. Also, the graphing calculator will do essentially all of this here for us. So at this point here, we're going to stop here for today.